Welcome to Ready to Derive. Let me present a scenario to you. Suppose you have a 60-point test consisting of multiple choice questions at 2 points each and shorter answer questions worth 5 points each. You can probably figure out that if we make X the number of multiple choice questions and Y the number of short answer questions, this equation must be true. If you're not so confident on this, check out my video on standard form, where we go into great depth about how to generate equations of lines in standard form. And here, let me present this then. There are 18 questions on the test. This generates its own equation relating X and Y, that the sum of those has to equal 18. Put these together and we have what's known as a system of equations. And while there are a lot of, infinitely many points that satisfy one equation and infinitely many that satisfy the other, we are looking for the one combination of X and Y that could satisfy both. And that's called solving a system of equations. So one example, that X plus Y equals 18, we could have 5 multiple choice and 13 short answer questions. But if we try and substitute those values into the other equation, 2 times 5 and 5 times 13, we get a total of 75, which is not equal to 60. So rather than cycle through all the different combinations and hope to land upon the one that works in both, that's what this video is about, how to solve systems of equations. We're going to look at it graphically and algebraically, the method of elimination and substitution. So stay tuned to find out more. So we are going to approach this solving this system from a graphical approach at first and then get into the algebra. So formally we should define X and Y, and these are equations. And since both equations are in standard form, finding the X and Y intercepts is the best way to graph them. So recall that the X-intercept is when Y equals 0. So if we put Y equals 0 into that equation, we get 2X equals 60 or X equals 30, comma 0. And that situation would mean that we had 30 multiple choice questions, each worth 2 points each, and no short answer. So while that's not a feasible solution, since we know this test has both, it's useful for being able to graph. And for the Y-intercept, we'd make X equals 0, and that would, if we did that, that would take this term out, and 5 into 60 would be 12, 0, comma 12. And again, that would be 12 all short answer, 12 short answers, and no multiple choice. And we can graph them, we can plot those intercepts. And technically, while the graph should really consist of dots, you know, I can put a dot on 17, comma 1, 1, comma 17, 10, comma 8, 8, comma 10. I shouldn't really connect them, but for simplicity, I can do that. And the reason I shouldn't do that is I can't really have fractions and decimals in terms of the number of questions. But again, since we're looking for one solution, we can get away with connecting it like this and finding where they intersect. So for the other case, if I make Y equals 0, I get 18, comma 0. So that's all multiple choice questions and no short answer. And similarly, if I make X equals 0, I get 0, 18. So let's plot those. Let's connect. And we see that there is one point where they do intersect at 10, comma 8. And what does that mean in terms of this problem? It means that the situation where there's 10 multiple choice and 8 short answer questions would satisfy this scenario. So graphically is pretty easy to do. Why would we want to do it algebraically? Well, what if that intersection point in another scenario was a decimal or fraction? It would be virtually impossible to find graphically. So let's embark on solving systems algebraically. So we're going to begin by solving systems using the method of substitution. So we'll take that same system of equations and see if we can generate the same answer algebraically. So the first step in substitution is to isolate one variable in one of the equations. And usually it's a variable that does not have, or that has a coefficient of 1. So you wouldn't want to isolate X, say in that equation, because you'd have to kind of divide by 2 and you'd end up with fractions. But what if, and we could isolate X or Y, so we'll look at this equation. Let's call this equation 1, this 2. What if we isolate Y in this equation? So we get Y equals 18 minus X. So we do that, and then in the next step, we substitute for this variable in the other equation. So we are going to substitute into equation 1. So equation 1 is 2x plus 5 equals 60, 5 times y, and we've just established that y is always going to be 18 minus whatever x is. So if we put that in, notice that we have reduced what we had was 2 equations with 2 variables to 1 equation with 1 variable. So what do we do next? Well, we know how to solve that. So we're going to solve for this variable. So 2x plus, we distribute 5 in. So 90 minus 5x equals 60. And we'll continue to solve. Negative 3x plus 90 equals 60. Negative 3x equals negative 30. And x equals 10. Oh, right. That's what we got in the graphical approach. Once we have x equals 10, we just have to substitute this back in and solve for the other variable. So now we might as well just use it in this form, y equals 18 minus x. So we'll do y equals 18 minus 10, which gives us 8. And that gives us the final answer, which we know from before. The final answer is 10, 8. We know that's 10 multiple choice and 8 short answer. Now there is one other step you can do, is always check that your solution works. Now it's easy to check in the second equation because we know 10 plus 8 is 18. We used that equation. So the best thing is to go into the equation, the other equation that we didn't use in the final step. So if we put 10 in for x and 8 in for y, the question is, does that come out to be 60? So that's 20 plus 40. Oh, that equals 60. We are done. So we're going to practice a couple of problems. So let's solve this system. So as you can see, sometimes the isolation is already done for us. So we see y equals 3x. We don't have to bother isolating. It's isolated already, and it is begging us to replace that y in the second equation with 3x. So let's do that. So we get 5x minus 2, leave a space for what y is in terms of x. So we'll rewrite that equation. Now we'll go in there and put 3x in there. So, and then simplify. 5x minus 6x equals 1. Negative 1x equals 1. So x equals negative 1. And then we go back and we know that y equals 3x. So y equals 3 times negative 1, which is negative 3. So we think that our answer is negative 1, negative 3, but we are going to check. So to check, we will go into the other equation, which is 5 times x minus 2 times y should equal 1. We get negative 5 minus 2 times negative 3, that's plus 6, which does equal 1, and we're done. Now, what about in this situation here? Now we see that the only variable that can be isolated easily is x in the second equation. So let's write that as x equals 9 plus 3y. Take the other equation, this time we're going to replace x. So 2 plus 5y equals negative 4. Go and put x in there as 9 plus 3y. And distribute 18 plus 6y plus 5y equals negative 4. And you can kind of do the rest, simplify, solve, and you will get y equals negative 2. Now we are going to go back and plug that in to find x. So 9 plus 3 times negative 2. And that comes out to be 3. So we think that our answer is 3 comma negative 2. But let's check. And so we're going to do 2 times x, so 2 times 3 plus 5 times y, 5 times negative 2. Does that come out to equal negative 4? That's 6 minus 10. Yes, that equals negative 4. And we're done. So before we learn about the method of elimination, which is the other algebraic method of solving systems equations, we're just going to practice adding equations together and see what crops up. So here's the system we just solved in the slide before. And what does it mean to add equations together? Well, since both sides are equal on both equations, if we add the left-hand sides and the right-hand sides separately, they should come out to be the same answer also. So 9 plus negative 4 is 5. And 2x plus 1x is 3x. And minus 5y, sorry, plus 5y minus 3y would be plus 2y. So what did that achieve for us? Absolutely nothing. We still got an equation with two variables in it, but now I'm going to do something, write something a little different. Now, what have I done here? Have a look over here. If you can see that the first equation is the same, but the second equation, I've multiplied both sides of the equation by -2. Why did I do that? Well, watch what happens when we add them together now. Notice that 2x and -2x, notice that they cancel to give 0. And 5y plus 6y is 11y equals, and -4 and -18 is -22. We get y equals, and we get one equation, one variable, which we can actually solve to get y equals -2. And then if we plug that back in, we could solve for x. And so we are discovering a different way to go about solving a system of equations. And we'll formalize this in the next slide. So we are going to take our equation, a set of equations from the 60-point test scenario and use this to demonstrate the solving systems using elimination. So the first step is to multiply one or both equations by usually obviously different numbers so that the coefficients of one pair of variables are opposites. So I'm thinking you could do this with x or y, but I'm going to do this. I'm going to multiply the second equation by -2 because I want the x coefficient to be the opposite for each equation. So this is going to stay put. 2x plus 5y equals 60. And this is going to become -2x minus 2y equals -36. So as we saw in the slide before, we're at a stage where we can add the two equations. And because of our manipulation with that -2, the x terms cancel out, right? So these are going to cancel out, and we are left with 3y equals 24, which we can solve to get y equals 8. That should be familiar. Sorry, I already went ahead and solved. It was the nice thing about elimination is a pretty easy solve. And then we are going to substitute and solve for the other variable. So now which equation should we use? It's better to kind of go back and use the untouched equation in case you made a mistake when multiplying by -2. So we have x plus y equals 18. So x plus 8 equals 18, which gives us x equals 10. That sounds familiar. Remember 10, 8. It was 10 multiple choice, 8 short answer. And as usual, you would want to check that your solution works, but we already did this in the opening scenario, so I'll leave that to you. So let's practice this one now where we do have to multiply both equations by different numbers. So you could choose to eliminate the x terms or the y terms. It's up to you. I am going to start by eliminating the y terms because one is positive, one is negative. So I kind of always like to not have to multiply by a negative number. So I'm going to multiply the first equation by 4 and the second equation by 3. And if that's not clear why, you'll see in a moment. So 4 times 2x, that would be 8x plus 12y, and 4 times 16 is 64. And then if we do the second equation by 3 on both sides, so that's 15x, and then minus 12y, which is exactly what I wanted. I wanted those to be opposites, is -18. So now when you add the equations together, these y terms cancel, and you're left with 23x equals 46. And so x comes out to be 2. And now we take x equals 2 and we plug it into one of the equations. So to solve for y, so to solve for y, maybe I'll just use the first equation. So 2 times 2 plus 3y equals 16. So 4 plus 3y equals 16. 3y equals 12. And y comes out to equal 4. So we think that our answer is 2, 4 to that system of equations. And then if we just check, now this time you want to check using the other equation. So you would do 5x minus 4y. So 5 times 2 minus 4 times 4. Does that equal -6? That's 10 minus 16 does indeed equal -6. And we're done. We're going to end with a real world problem. When I say real world, I mean like really. This was a problem that I actually solved when I was staying at a vacation home. I needed whole milk for baking, but I only had low fat and cream, and the supermarket was like at least 20 minutes drive away, so I just didn't feel like going out and getting whole milk. So, and I needed 1.5 cups of whole milk. So this is, I mean, probably most normal people would have just like approximated, right? You figure you need 3.5% fat, so you probably want more low-fat milk than cream. But being a mathematician, this problem was intriguing to me, and I wanted to solve it exactly. So I made X as the number of cups of low-fat milk, Y the number of cups of cream, and I needed 1.5 cups in total. So I knew I had this. 1.5, and I know that my X cups of low-fat milk would contribute this much fat, 0.02 X, and the cream would be 0.10 Y. And this is the tricky bit. So you want your resulting cups to be 3.5% fat. So we know that decimal is 0.035, but you do realize that that is of the total number of cups that you desire, which is 1.5. So let's see, I multiplied these together to get 0.0525. And now, because I don't really like dealing with decimals, I multiplied the second equation by 100. So I got 2x plus 10y equals, and that would be 5.25. And you could choose to do the method of, elimination or substitution. I kind of like substitution, so I isolated y equals 1.5. I like substitution when it's one of the variables can be isolated effectively. So and then I just did substitution. So I will have 2x plus 10, and y was 1.5 minus x equals 5.25. I will leave the solving up to you, but when you should get that x equals 1.2, it's kind of approximately 1.2 actually. So 1.2, and then solved for y, and I got y equals 0.3 approximately again. So I knew that I needed 1.2 cups of low-fat milk and 0.3 cups of cream to perfectly answer this problem. Well, I hope you enjoyed this video. If so, please do like it and hit the subscribe button, and see you again soon.